Okay, recording is running. So to create our own array class, first, of course, we will create a new project. We will create a console application. We'll call it my array. And what we also, once we're done with the basic functionality of the array, or maybe from the get-go we could do is we can implement the array in a way that it's not done by STL. So the way STL does it is that if you copy an array, or any of the objects, be that a string or a list, it always does a full copy of the object, which mostly has historical reasons why they chose this. Although it's also helpful to avoid various potential issues with regard to usage. If people are using the functionality without reading the documentation, a approach that always creates a full copy is more fail-safe. But of course, the downside is that you always need a lot of at least some computation to create a copy, and then of course you need additional memory to hold the copy. So what we will try to do what we will try to do is we will try to implement our container array such that it uses a copy on write mechanism. Copy on write means that when you create a copy of the object, while from the outer object, you of course have to make a copy. Everything internal or the internal states remain shared. And only once you decide to write to one of the objects, it will then make a full copy because then it needed to be able to modify it. There are of course some operations which might be read operations, but they are ambiguous. So they might also create cause a write, so they will also trigger a copy creation. The main advantage of such such a mechanism is that when those objects are used as arguments or as return values, then it's really easy to save on all the memory and computation, because if you're just passing it as an argument, it just makes a quick shallow copy, and then the internal states remain unreplicated. Yeah, so let's start. Add class my array. File name is also fine if you let it as my array. Okay, class is created. What we could do as well, right. What we could do as well is we could add here a new C++ file name where we'll just move the content of the old class here. And we could also use this namespace feature, I think I explained that already, of C++, which allows us to separate things into individual namespaces. So we will, let's also create here an empty folder. Although as I think I mentioned in one of the very early lectures, the folders created here are just like filters. They are not represented. They're not representative of the file location in the file system. So even if you move those things here around, if we copy the path and then go there. Oh, sorry, that was not quite what I intended. To move the file name. Then we see that everything still is in one folder, even though here those elements are in different subfolders. With other languages, as mentioned, like C#, that is not the case. Then it really moves the file around. So this here is more of a convenience filter approach. Right. So let's start with the namespace. So, we'll call it my framework. That sounds as good as a name as any other. Although we can use, so first of all, using these brackets by default creates indentation. So what we also can do is we can hash define ifb begin, and then we move the functionality into this preprocessor definition. Then This will be n. Then we have the same functionality, but the auto formatting just treats this as a normal statement. So it now doesn't try to indent for us the actual class. So this you will find such approach quite often. For example, the Qt framework excessively uses such trickery. So the preprocessor is really a very versatile and useful thing. Although we can also do one better. We can create here another file, h, and store those things here, because if we would decide at some point to create something else that would still fall into this namespace, then it's nice to have some shared defines already defined. Okay, we have this. We have the class here. The first thing we want to make this a template class. So template T. For an array, we don't need more than one type. T, we could call it V like for value, because then if we would create a map at some point, maybe if we have time, although I think that would be outside of the scope, that might be too much work. Then we would use V and K, so V value K key. So this helps us to keep the already now created code a bit more generic. Of course, we could also have some sort of abstract container where we outsource some of the functionality, but that would, I think, complicate things too much. So let's just start with this. So what do we need for our array? Of course, we will need some constructor. We need to define things as public. We need the constructor. We need the destructor. We could create another constructor that takes account so that it can pre-initialize an array with a certain size, but that's for later. We will first just create a function that gives us that we can use to create some internal to reserve some internal memory. We'll just call it reserve or something like that. It will be for later. But what we also need definitely is a constructor for copying, since we want to be able to copy our array. So my array should be const. My array reference other. All right, and we don't need a C++ file for this thing. Since it's a template, we need to write everything in the header. Okay, so we have our constructor. Then we will also want a what's the name of that? Move constructor that is used when you return a value. In which case, if you have such a move constructor available, you can save on some operations, and this is not const by nature, since usually you are not returning const objects. Okay, that's all we need here. So let's we'll of course add some bodies to the functions here. We are not just writing down what we will be needing. We will need an assignment operator, obviously. So array reference my array reference equals the typo. Again, it takes a const other reference, then another one takes non-const. But we need that I can move operator here the same way as we did with the other one. Then we can later also define class equals and as equals once for concatenating two arrays and once writing just one element. The same then also just a plus operator, which we'll do that much later. What we definitely want with a array is to be able to access elements using this square bracket operator. So const value type reference of the square bracket. And we can, in principle, with the square bracket operator, use anything we want as a index. So as you saw with maps, with the CD map, we can use the square bracket operator with a string or with anything. Since this is an array, obviously just indices make sense. So size t index, this one is const. And then we make another one which is not const. And this will be quite an important distinction because depending on whether the const or the non-const version of this operator is invoked, we will either trigger the copy on write or not. So this operator can of course be just used to retrieve some data, but it gives us a full writable reference. So we might also change the data. So at this point, it is mandatory to create a deep copy. And the way we will implement here the mechanism of copying is such that we won't need an explicit synchronization for multi-threaded security. So this means we will use mechanisms here which are implemented such that you can access the variable or any of these variables from multiple threads with regard to making copies and assigning them. Of course, invoking more complex operations on the same element would not be thread safe, so then you would need to create an own copy of the variable. But the important thing is that just to create copies, you don't need to explicitly synchronize, which is a great help already. And of course, if you would want some really thread safe container class, then that would make things more complicated. Usually, you probably would not want to access container classes in a multi-threaded manner anyways. Plus, this also breaks some other functionality, which we will implement a bit later. So I think such a copying and assigning is fine. Everything else not is a good enough compromise for asterisk. It's a typing const asterisk. We require data, so this will be a const. It will just return a data to the internal pointer. To the internal data, so it will return a pointer to the internal data, and the way it's made, it will assume that we are, let's call it const data, are not modifying it. But in case we want to modify it, we can create another one which is not const, which is just called data. Okay, then of course we want to count. Size underscore t count. Const tells us how many elements we have. We might want like a convenience function for this empty, which just returns, which is const, and we can implement it instantly because it's quite trivial. Return count equals null. If it's empty, then it's empty. That is as simple as it gets. And we might want another function similar to count, but called capacity. In case we have pre-allocated additional memory, then we would use this to check how many elements we can still put in there before some reallocation. What is the typo? Before some reallocation is needed. Okay, and of course, then we would want to add this reserve function. So, right, reserve size t. Oops. Size t. This is the capacity. And what also is quite useful is a void clear, which just removes everything from the array. It just resets the array. Okay, I think everything else will be to be done in time. We'll add the support for iterators later on, but not now. Okay, so let's see. So we have the most basic functions. You can reserve some capacity. You can clear the content. You can check if it's empty. You can find out how many elements there are. You can access elements. All right, and we will also need, of course, something to add elements to the array. This I forgot. So let's add some append function. Void const the reference value. And we also will make another append, which we could call it merge, which would allow us to merge multiple arrays. But that can be done later. So let's switch it fine. And we could make also an append which allows us to add more than one element at once. So this one, the first append just allows us to add one element, but here we'll make another one, const asterisk p value and count. With the other one, we can specify, we can give it a pointer, the standard C array, or to what we get as data from another array, and then do the merging. So this will already help us quite a lot. Okay, I think now we have everything that's really needed. We might later want to add some convenience functions that we don't need to use the square bracket operator, but we might want to add a get add or something like that, but that is for later. What else is nice? Maybe like get first, get last, and so on, but these are our convenience functions. Now let's implement the main functionality. So protected. Let's see what we want there. Now, obviously we need some internal data structure to keep the information that are stored in our array. So let's call it yeah, we would call this C my array, then we could call the structure as my array. We can just call it array data. We don't need to overcomplicate things. And what will be important here is that that a instance of this data array will be shared amongst multiple instances of our array, assuming that we have created it's just my data, that we have copied it by assigning or by creating a new object from an existing array. So what we will want internally is a reference count. Yes. Initialize it to null. I declare that we don't have right include have long. We could use just unsigned int here, but long is nice. So let's. So we will need the Windows include for the later part of this mechanism. So I declare the variable as volatile, which means that the compiler will not generate any caching of the variable's value. It indicates that the variable might be accessed and modified by different threads. But of course, to be really safe about it, we will need to use special functions. We cannot just use like plus plus or minus minus or normal mathematical operation. They still might be broken up into multiple individual operations, and the thread scheduler of the operating system can interrupt it at any point. So we will use special functions, which use special hardware instructions, which are atomic in nature. Even if they are complex, they cannot be interrupted by the scheduler mid in execution. They either are executed entirely or not executed at all. Okay, what else do we need? We need some count. So size t count. And of course, we need the capacity. So as you see already, some of the functions will be just referring to values in my data, and of course, checking whether those values exist. And then last thing we need will be an array of our values that are stored in our array. So v data. And what we do here is we kind of create an array of size 0. And the idea is that later, when we create the actual object, we can create a bigger object with malloc, and then we'll already have the needed memory for everything. And maybe to be more fancy, we'll use a more space-saving approach, PTR. So we will do everything. Yeah. in one line. You could, of course, just break line and then write again my data asterisk ptr equals null, but this is also nice to see, and it saves you on some lines of code, so maybe you like it. Also, even more space saving like this. Okay. So what we, and then of course, this will be the only variable that our class here will be holding directly. So the size of class, assuming we don't make anything virtual here, will be just the size of one pointer. Meaning that it can be very conveniently returned even using the Rex register. So it doesn't, the compiler doesn't need to use the first argument to pass a reference. So it's a very elegant approach. Okay, so let's continue first thing. We will need will be something to create those data. So we will create a function, the type my data asterisk make data. We will give it a capacity as an argument so that we know how many elements should be stored in this array. Right, so asterisk ptr is equals, and we need to use the malloc function since we need to create it. So if we would use new on this thing, it would just create basically enough for those. So it would allocate only enough memory for those three variables, but we want to add additional size. So what we do is here malloc size of data plus capacity multiplied by size of W. And this way we create a memory block which contains here our header data and all the other data that we want. We notice here that I used this inline initialization. So if we just malloc something, it won't run any constructor be it an implicitly or explicitly created one. So what we need to do is we need to use the new operator, pass to it the already allocated memory. So if you pass a memory block to new, it will use that memory block instead of invoking malloc on its own. And then of course we need the type. We want the constructor for, since we don't have here an explicit constructor, it will just set those three things to 0 and that's it. What we also could do is we could not initialize anything and then here use memset on the whole object and just memset everything to 0. But this approach is more efficient since we kind of don't need to memset our data. Anyway, so last thing to do once we have initialized the thing, we need to set capacity to the capacity. Given that we only have two more, one could be here much more manual, just assign the other two variables to be 0 and be done with it. But we will need this later on, so it's nice to demonstrate it already here and then return, of course, our pointer. So at this point, not much happened, but what we want to do is we want to create another function which will actually invoke this function and then assign it to our variable. So we will call it alloc and takes again capacity as argument. So this one here can actually be a static function. It does not access anything that would be defined on our current object. But for now, let's leave it as is. We might want to later add the ability to specify some custom memory allocator, in which case we would need this to be able to access already members on this. And of course, then the whole thing would be bigger than size of pointer. So we will leave it as is. And here, it's actually quite simple. Just here it equals make data from capacity. And what we'll do now is we'll invoke another function which we haven't written yet. It will be called attach data. typing data and give it this empty data pointer. We could, of course, add here a check whether malloc was successful. So if it failed, then this would be null. But for now, let's not spend too much time with adding too much error handling, as this takes time away from the more important things. So the next thing to do is to create our attach function, which takes a pointer. And what we also will create will be a detach function. So we'll just call it attach. The data is fine. Right. Attach. Data doesn't take any arguments. And detach data is invoked from attach data. It's a cleanup function. It's of course also invoked from the destructor here. If we want to detach from the objective needed. Okay. So at this point, once detach was called, we know that MPTR will be null. So if there was a reference, it was cleared, and if there was no reference, then nothing has been done. So now we check actually whether pointer is not null, because the way the later implementation will work, it will allow us to for the pointer to pass to attach data to actually be null. So in this case, it's equivalent to just calling detach, but we don't want to have this distinction in every function. Instead, we want to have the distinction one level deeper. This allows us to save on redundant code and doesn't really add any additional complexity. So it's just an improvement without downsides. So here, since we know that the MPTR is null, we can just assign it. And now the very important thing, we need to increment this counter. Obviously, if we are doing this and the counter is 0, then we could just make is equals 1. But we will use the attach function also when attaching this data objects from other instances of the myArray, so that the value already might be incremented, and actually it might be held, other references to this element might be held by different threads, which do whatever they like. So we will use a function which is defined in the Windows age. If we would not have a Windows at our disposal, so if you would write for Linux, then you could use a object from the STL, which implements this functionality for every platform. Or you could just use platform-specific functions from whatever Linux framework you are using. Those functions here invoke hardware instructions of the CPU. So even though they might be called differently, they will be available on all in all frameworks one way or another. Maybe not identical. So the STL version is more complex. It kind of creates a class for it, while here it's a very basic approach with what Windows offers. But since we're here writing on Windows, let's just go with it. So it's called interlocked increment. Oops, interlocked increment. And then you see here it takes a pointer to an unsigned long. Just use normal long. It should be fine. Let's see. So we take our links, reference or links, we add here and refs, check in column. And what this does is it will increment the value, and it will ensure that even if two threads at the very same time would try to increment the value, or one would try to increment, the other would try to decrement it, or whatever, that we will here always end in a consistent state and not have a situation where kind of two threads try to increment at the same time, both create some sort of intermediate copies, such that the result of the implementation, once it's saved, would be missing one of the effects, since both did an implementation on a local copy. So in the end, the value ended up being incremented by 1, while two threads doing an increment should be incremented by 2. This approach is implemented. This interlocked increment avoids all these issues, and it does this in a very efficient way, since it uses special hardware instructions it is very fast. If you would guard the variable with a mutex or some other object which would rely on operating system mechanisms, that would require a few context switches, so it would not be efficient by far. And this way is almost as fast as a normal incrementation operation, just a nanosecond or two more of operations. So as you see, the attached data is quite simple. Now let's see the detached data. So first thing, of course, we do here is we check whether MPTR is not null. So if MPTR, then we do something else we already done. And at the end of what we are doing, we can set this to 0. And what we want to do here is we're using yet another function. So if interlocal decrement, this conversion just interlocal decrement, and this again takes a pointer, but it is a quite an interesting returns as the last value at well, not the last value, it returns as the value that in the end ended up it returns us the final value which was the result of the operation. So this equals, if this is equals 0, then we will do some more things. This is at this point a bit more convoluted because other implementations of this mechanism might give you not the value that that ended up being the result of the operation, but they might give you a value which was the value that was last stored before the operation took place. So if you would be using, I think, the Qt version, so the Qt framework is also such operators, such operations, then there I think it will return you the last value before the operation. So in this case, you would check if it was 1. Here at the testing whether it became 0, while before we would be testing whether it was 1 before the operation was executed. So basically what we want to know is we want to know whether this was the last reference to this data. So if reference to this shared object anymore. So this gives us the freedom to do with it whatever we want, to get rid of it. And this will be a bit more, this will require a few more steps since we have now to handle not only the object itself, but also the data in the data. So we'll implement a loop for size t, e equals 0, e is less than ptr count e plus plus. And now what we want is we want mptr data from I, and on this thing we'll call the destructor filter p. And the fact is that even if the type would be some basic type like an integer, we can call it a destructor on it. In this case, it's just a non-functional because for the integer you don't have a destructor. But this implementation here will work with any type. And of course, then, so we use here new to initialize this, but since we don't have anything else to handle, so there are two ways we can get rid of it. So one is, of course, that we, for the thing itself, also for the destructor, but this, as mentioned, will not really do anything since there is nothing to do, but for completeness, let's leave it like this so that you know if you would add here a complex. And then, of course, the last thing to do will be to free the memory that we have allocated. So free PTR, and at this point we are done. The detach operation is completed. If we had the last reference, the object has been disposed of properly. And when we will be needing to create a new object, we'll be just using this alloc function. So let's not waste our time and start using this. So let's maybe start with the append function. I think this is useful enough. So we can be place here and reuse the other append directly. So append reference value comma 1. This means basically that our add one element function is just a convenience function, and generally usage expects us to use the normal append function. And here, first thing what we need to do is we need to ensure that we have enough room, so that capacity is large enough. So we will either check directly or we will just call reserve. One approach that we can utilize here is that we make it such that we can always call reserve, and if the reserve itself will check whether actually it needs to reserve something or whether it's fine. So we reserve, then we of course need to check whether pointer is null, since it might be if this is the first insertion. So if this is not null, then count, and if it is null, then it's null. If there is no object, then it's null. Reserve will be smart enough that it will be able to handle both cases, whether there is or is not an object already allocated. And we need to add, of course, here the count of elements that we want to store. Okay, error handling is something for later. And at this point in the code, while reserve doesn't yet exist, but if it would be, we would already know that our array is A, by now exclusive. So reserve automatically will assume that we want to modify the array, and it will create an exclusive copy. And the second thing is that it will ensure that we have enough room to store the data. So now we can make a loop. We lazy and copy the loop from below. Just need to change it slightly. Sec. Here we just go to the count provided. Okay, and now what we will need to do is we will try to invoke the copy constructor on the new entries. So new, we need to pass to it the memory, so ptr data plus mptr count plus I. And as you should remember, when we add a integer to a pointer, then it increments the pointer not by the integer size, but by the integer count of sizes of whatever type the pointer is. So basically, it should be an I, not a 1. So basically, here we will first access the memory of the first free slot in our array, then the second free slot, and so on and so on. And of course, since this is supposed to be the copy constructor, we need to pass to it the value at I, so that it creates a copy for us. And such copy constructors are by default available for all the built-in types. So it will work just fine with the simple data types, as well as it will work just fine with complex data types. And then once you're done, you can increase versus equals count. The other option would, of course, be to increase count at every go through. But I decided to do it this way. It's not really a relevant decision with regard to optimization. Okay, so now let's see and maybe we also quickly add a body to the clear function, and we already feel like we achieved more, which is always good. Sometimes when starting a large project, the amount of work needed might seem unsurmountable. So in such scenarios, it's actually quite a good idea to start with some small things or things that will give you as quickly a feeling that you have achieved a lot. So especially such simple functions, we should make them as fast as possible. So in our reserve, we will first check the case whether this is an entirely empty object, so there is absolutely nothing. So if this is null PTR, then we just look capacity, and that's it, because there is nothing else to do. Next case, we know, okay, there is already some memory allocated. Let's check whether we actually need to extend the amount of allocated memory. So else if, and there are two cases when we kind of need quotation mark to do it. One, of course, when we really need to do it because there is not enough memory, but the other case is when the memory which we have is unfortunately shared with another object. So here, we will first check refs. If this is greater 1, then we cannot modify it. So we need to make a new copy, even if the block that was allocated initially would have been large enough to add an element. And the other option, so using or, is if m underscore ptr capacity is less than the requested capacity. And the else case is just all fine, nothing to do. Oops, I did not intend to make this case. And just use the Control U hotkey to just make it larger. So, depending on how we want the whole thing to work, we might either just always allocate the capacity requested, or we might want to actually allocate more capacity than what was requested. And I think this approach gives us better performance. So let's say with a new variable, extra capacity, which will be equals to capacity divided by 2. Okay, and yeah, and we could also give it some sort of upper limit. For example, if extra capacity is more than 1,000 elements, then we will just cap it to 1,000 elements instead of really always wasting half of the memory. So if we only need to reallocate every 1,000 insertions, it's already very little, it's just 1 per million. So it will not be detrimental to our performance. And to actually do the reallocation, we will invoke a function which we will create next. Realloc. And realloc just gets the capacity plus extra capacity. Gets capacity plus extra capacity. Okay, so now we need to create our realloc function. Alloc, let's put it here. Void realloc st and capacity. Okay, so first thing, of course, we need to create new data, and then we will attach those data. So we can copy the contents in here. Make data from capacity. Do we want to change? We could make it such that if we invoke the function and the existing data are already bigger, that then we go with the existing data. But that let's not do it for now. For now, we just go with the requested capacity and don't add any fancy additional mechanisms. So we have created a new larger block. We know that it is count plus something. Although if we go this way, we would we could run a situation where we have a bug somewhere else that then realloc would create a smaller element, smaller data block. But let's say that is fine, because if we would want to shrink the thing, then we would want to actually discard things. So let's really keep it as is. What we need now is again a loop, which will go through all the existing elements, and we need here a safety. And I is less than MPTR capacity. Because if we at some point created a function which would call realloc to truncate the data and really remove them from memory. So typically a truncate function would usually only remove the elements by changing the counter value and not really, well, it would of course invoke the destructor for the elements, but it would not dispose of them, of the memory allocated for them right away. Of course, it depends. You could have an implementation which operates such that it would dispose of the memory if the amount of memory to be freed is above a certain threshold. So if you can save, let's say a few kilobyte, then you would do it, or if maybe megabyte, depending on how memory critical your application is. And if you cannot save much memory, so it's like if you just trunk it by one element or by two elements, then you would not do anything. Or you could also make it like our extra capacity to say, if the capacity is more than twice the data that are held within, then we truncate it, since probably that capacity won't be needed anytime soon. So this can be done however we want, but here let's keep this fail-safe to ensure that we will not try to read something that does not exist. And as you might already surmise, we can here use the copy constructor just differently. So here, of course, we are starting with PTR data. The initial PTR data count is null, so we just start with plus I. And here as data, we use then MPTR data. This way, we will create a new object. So we really, so this really is somewhat a labor-intensive operation, since if we would, for example, use std strings, then here we would basically create a new strings copy of the string data. So that would require copy operations as well as many memory allocations. So next thing, if we have time to implement, would be of course an own string, which would use the same mechanism, this copy on write mechanic, which then would ensure that this assignment here would be super fast. One thing one might think would be a good idea is here to just use memcopy, but no, it is not, because your elements which you might hold inside will have internal references to things. And if you just copy the outer memory, then you would create issues. Like if you would memcopy our my array and it would have and create a new one this way, then it would not increment this reference counter. So it's really important to use the proper constructor and destructor here. Okay, so we have resized, we've copied the things. Now the last thing to do is to set the pointer count to count to the count. This one. Tack. And then what we do is we just attach the new object. And as we remember, attach will first detach the old thing, and then it will attach the new thing. So those functions working together, those function alloc, detach, and attach, will ensure that once alloc is done, realloc is done, we are left with a new object which is large enough to hold whatever we want, and is now held by us exclusively. If we would have like a situation where one element in one object in one thread is just creating this invoking this realloc function, while another thread is just now disposing with detach of its data, this will be properly handled by the detach function. So either we or the other object will invoke the cleanup code. The way this interlocked functions work is that we should not be able to maneuver ourselves in this scenario where, for example, none would make the disposal or both would try to dispose at the same time, which would of course not be good. Okay, so this already is some basic functionality. So let's try a test case. We already have included it. So FA, or did I call it my FA? My FA, okay. So my FA. array. It's like a str, just self-made. And let's make it of int. My int array. Okay. Append. Let's do this in loop 4. Int e is equals null, e is less than 10, e plus plus, and then of course append e. Oops, e, not one. Now that should work and be reasonably boring. So let's just run it and see if it doesn't crash. That's always a reasonable first test. And something p-value. I have a typo there? No. And what's the pointer? That should be fine. Now what does it look like? Doesn't like this to the claims that PTR is unexpected. That is odd. I use capital P. No, that's normal P. Let's see what the actual output says. Instead of just looking on those things. I have a bracket somewhere which with the word stuff and reserve. It's nice. Ich Konstruktor. Okay. Oh, yes. I forgot the name of the type. Of course, I need the name of the type here first. I did the same mistake somewhere else. Yes, I did it here as well. Obviously, when we use new, we still need to tell it which type and then which constructor to invoke, and we can pass the element. Like this. Let's see. All right. I use the wrong type. Of course, we need the V type and not the my data type. Now it's fine. Okay. Great. Now it's complaining that we have not implemented all the functions. It's missing the constructor. So this constructor is pretty much just empty. So we just create an empty bracket. The other ones. So if the functions are not virtual, we have another bug somewhere, but it's already better. Let's see. Go and repeat. It should bring us to the debugger, but kind of doesn't. Let's try unpacking. In principle, this should bring us to where the error happened. So let's just step through the whole thing. 9, 5. So first time, second time, third time, fourth time. We have somewhere not allocated enough memory. Let's review it. Make data type of memory. Oh yes, that should be an asterisk here. My shift press wasn't strong enough. 9, 5. Yeah, now it's fine. And if we look here, data, copy value, value. Int asterisk, int asterisk, and you can int asterisk now use the square bracket operator to inspect the value. So 0 is 0, 1 is 1, and so on. So our data are correct. And now we would want some mechanism to access them. So first, maybe let's add some meat to our other functions. So capacity just return this already. We need to check whether PTR the value that's stored in PTR. I think for capacity we have had this already somewhere. Oh, the final operator is, well, we did it for count, but that is more or less the same thing. So x, and just make sure count plus count, and count also needs some. Okay. Oops. And our capacity is identical, just that here it takes capacity. Okay, data we also need to do. To access data, the other things as well. So we also need a function that makes one of the that makes it exclusive, so that we can return a pointer that is modifiable. Let's create a function here somewhere, or maybe at the very end, make exclusive. Make exclusive. Check. And here, since when we call make exclusive, we expect to be able to access the data. So we'll copy this thing, our reserve, and just change that capacity basically just here 1, because we want it even if we don't use it. So we just want one dummy entry, and here we just go with realloc. It will just contain the capacity that was stored in PTR. So this check here is of course not needed. If we go to make it exclusive, then we always do it. And here we just go with PTR. Oops. PTR count capacity so that it doesn't change anything except just copying everything as it was. So we get the same capacity, we will get the same elements. It is all more or less identical. Okay, so data const is super trivial. Just we can actually just copy another thing. So data const will define such that it can return a null pointer if there are no data in the array. And since if there are no data, we would get count 0. Should not access anything here. The other data is a bit more convoluted, since it first calls our maker exclusive, and then it returns PTR data, because we know that it will at this point exist. Even in principle, we could also make this make exclusive here alloc 0, since we won't access those things either. Yeah, that should be fine as well. We might want to change it later on if we see that usually when exclusive is called, we will want to have enough space for this one element, so that would be an optimization. But now, to be as precise as we can, we will use this approach that we just give it a 0, so that it creates just a useless my data that cannot hold any actual data. Just one is there to interact with. Okay, so at this point, we could already here use a loop and then access through those variables. But since we are so close, we could implement our two square bracket operators. So let's do that. So the below one will be just again make exclusive. very similar to this thing. Oops. And just that here we use the index on our data array. Oops. And the other one just does this without anything else. So the important thing to note here is that the way this copyright mechanism works is it really ensures that only for write operation, the data, the actual data, that only when you make a write operation, the object on which you make the write operation gets some data altered. So if you're just using read operations, we can just access the data directly without any special safety precautions. Of course, when we get a pointer which would be alterable, we need to ensure that it will be exclusive. And in this case, we would get here an invalid reference if this would be, let's say, I don't know, bigger than what is allowed. So in the next step, we should get here a to do. Row and add only. That's the wrong. That's the wrong order of operation. Add a bounce check and throw an error when needed. Exception return. So that we don't return a reference to an invalid memory to a invalid memory. But this we'll do later. So now our array is already functional, so we can print it, for example. So we go here onto my array count. Check and we need something to printf. Hash include stdio printf. What's in the backslash, and we don't need to call this anything. Just print the data and done with it. So my array here from I. We don't need the breakpoint. Let's run it. Okay, we're back somewhere again. Without the brackets, if we just then okay. PTR, that's a pointer, right? Why does it say buffer overflow? Says it's just a warning. Should be fine. Should not expect there being an overflow. Let's see the real errors. The real errors is that we forgot here the semicolon. I think there was a second error, yes. We cannot use count as a name, so what we can use is not so elegant, but it will work. Because we already used the same name here, count, as we are using here for the function. We'll rename this to get count or something like that. But you can also use this to specify where to look for count, and then it will be fine as well. And it printed properly. So we already have an array, which, well, it's not yet copying or assigning or anything, but it at least is able to hold values. So this is a good starting point to jump off from. So let's create a helper function called assign for assignment operations. In principle, we could also make it public here. I think our approach should be to keep as little functions public as needed. So if we have the assignment operator, we don't need a assign function, just adds confusion. The use case where you want this, there might be. Yeah, let's make it public. There is a use case where you have a pointer, the thing, and you would want to assign something you cannot assign to a pointer. So we need to asterisk pointer in brackets and then it's equals. It is much more easy to just write pointer, arrow operator. In principle, you could make pointer, arrow operator, and then operator equals open brackets, but that's ugly. So let's just make your pointer, arrow operator, and then assign, and then whatever you want to assign. So void, and this will just take an argument of this type, sec. And before we use the function instantly, it's not a long function. Just does attach data. Attach data. From other PTR. So it's really a one-liner, but it's useful. And we don't want to expose attached data slash publicly. So this is fine. And again, if you would use some special own memory management approach, you might want to assign other variables here as well. So if we would have a variable that holds a pointer to our memory pool, then we would need to assign this as well. Hence, we actually want this assign function, not just call attach data from the other places directly. And in the other places, then of course we can just use like stuff from this and stuff. It's a bit laggy today. I have the feeling. Assign other, suck. Then from our assignment operator for normal one, just we need to return asterisk this. And then you will of course also need to take care for our move operator here. And since it's a move operator, what we do here is just mptr is equals other mptr. Mistake other, I think I did, maybe not. And then for in other mptr will be set to null. PTR, my pointer. So we basically just transfer the ownership of and don't need to change the reference counts because now we are the owner. And of course, during the execution of such an operation, there is no expectation that the variable would be accessed by multiple threads at the same time. Okay, and of course here again, I think we need to return this asterisk. So let's just do that. Stack. Okay. Okay, so at this point, we can now create a copy of a variable. Let's call it my integral2. And my integral2 is equal to my array, and here we will use my array2 instead. That's fine. Okay, something is like 98. Should be a dot. Good. So as you see, it still worked. So the data were available. Now when we inspect those two, you see that it copied the data actually. So since we used here the operator and this was not explicitly defined as const, it assumed it needs to make a copy, even though we only used here a read-only access. So what we can do is we can. So normally when we would be using arguments or something like that, we would just pass this as const. Const see my array. So what we basically create here is just a const pointer. Then if we use this here, and it will know which operator to use. And now, as you see, all three instances of the one instance is kind of referring on the other, are using the same internal object. So the data are not duplicated. To maybe make this more illustrative, could here have a function like int array, which will have a const array, but without the reference. Wait, it's not correct. So add the type as well. So since this is not a reference, it will be created, and we will end up with a duplicate. But since it's const, when we use the square bracket operator, the thing I must know. Actually, we can make it even better. We'll make this just reference const, and then here we can just use our array tool. So we make the copy explicitly at the top. Then we pass this here to a function that takes a const value, and since it takes const, it will know which operator to use. So here, so we see both are still using the same data in memory, and the block was not reallocated. So given that this square bracket operator access is a bit ambiguous, it would be convenient to add some get value functions or just value add, something like that. That would pretty much just do the same thing, but by having different names, it would allow us to explicitly choose which operation we want to do. So let's add it here. Let's call this one get const, and the other will be just get or add const. Maybe like this. Add will be the one, and the other one will be const add or c add. That is not relevant. And since they do the same thing, we can now here just invoke those functions instead. If the compiler decides to make a copy of those functions, or if it decides to actually invoke them, we might want to see this, but it's even if it just leaves them where they are, it will not add any substantial overhead. So just one simple function call is very quick. So this is fine. So this way, we have here some additional convenience functions. Maybe you could call this add or let's leave it as is. We don't need to spend too much time on thinking of the best names for our functions. They are good enough as they are. And we forget to implement something. No, we already have everything here. Right, well, it goes here. So let's quickly add them. They will be just obviously invoking the the append operation. Not quite. We didn't add the merge function. Although we don't need merge, we can always use this append here. So let's do this way. So plus needs an array reference. My array reference. My array reference equals. And why it's just one element. It will be a const p reference space value. I wrote other arrays more. I should write it big for consistency with the other nomenclature. So let's use this capital here. Here, 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 and here, and here, and here. Okay. Right. So one takes value, the other one takes other. Right, so, and here just we'll be using the append function. So, and oops, and value, and you can asterisk this. Say something. Operator const value return this. I think it should be fine. It's just complaining for no reason. Right, and the other one is not yet complete. Or probably it was complaining because it kind of felt that it cannot properly pass the whole thing. Oh no, I have a typo. Now it's fine. Right. So the other one will use append from other const data comma count. Okay. And then we want also the plus operation. The plus operation is different since it does not since it returns a new object. So, oops. Yes. Get that goes away. And then we will just create a new object. Oops. What do we call it? We can call it just new with a capital N, since with a capital N it's not taken. My array. Here. Let's call it 10, but doesn't matter. Is equal my array new from asterisk this. Then new append and return new. And the other one, of course, needs to be changed the same way. Okay, good. So this functionality is done as well. Okay, are there any questions? Okay, if there are no questions, then let's continue. What we want to enable our object to do next. I think the next thing to do would really be to implement the iteration so that we can iterate for the array. For much later, what we could also implement would be something to get like sub arrays, so like a mid function. It gives us a section from the array, so starting and ending in an offset. Might want to have a remove and an insert that allows us to remove elements from a selected position or insert it there. Might also want a find function, but that's for later. What we now want is we want iterator. So as you remember from the last lecture, where we used the STL containers, we had these iterators, which you could use. And I'm actually not sure that I showed this to you. Let's quickly review it. There is a way to implicitly use them. I think we always use them explicitly. I don't see an implicit usage. So if we go to one of our iterators like here, we can do more or less the same thing for auto, oops, auto e, double point, container, double point, container, and then we can use it the same way as we would use it here. So this might be a notation you might be more familiar from Python or something like that. So that generally just the idea that you can have a for each type of loop without too much manual work. So this is much more convenient, but internally, we just need to have the support for this normal iterator mechanisms, and it just expands this into that. So I forgot to mention, but today we'll try both. So obviously what we will need will be a own object, some iterator type. So talked iterator, and our iterator needs a few things. So it will certainly need a constructor. What it will do will remain to be seen. Oops. It will be important. So iterator reference plus. Then we want plus equals is nice to have if you want to advance by a large amount of entries. So plus equals plus equals, and it takes a different type. So you can plus equals like anything. My network is today somehow laggy, so I'm sorry about that. Right. So we hit operator, it takes argument as a size. Oops. Size underscore t count. T count. So this one, what it will do is it will allow us to advance a data iterator by more than one position. Then we need the reference to asterisk, the asterisk operator, and we'll need the error operator as well. Just as the asterisk here, and here is the error. We will need to be able to compare it. So bool Operator ungleich. Where's the contact? Nice, I think. Const other we can copy somewhere else. Hello. Some technical issues now. The mouse is not clicking in the virtual machine when it's like. We connect our connection here. That should maybe fix that. Then that's covered. Can you hear me? I think the summer is summering too much. My laptop just crashed, but luckily our virtual machine is running on a server, so it didn't crash with my laptop. I just need to connect. Okay, it should be working again. Can you hear me? Am I back?
Yes, I can hear you.
Okay, perfect. Yeah, okay, so we go here, suck. Right, equals and unequals operator, both. Equals unequals here, so now we just use the equals one. Okay, good. And then we need some probably protecting variables. Let's see what would be useful. We need a variable that will hold a reference to our main internal data structure, or MPTR. And we will also need a variable that will hold a reference, a count, a index of where our current iterator is right now. Let's add those. Now we need to ask one more thing. We will need to define my array as friend so that we can access it. In my array, and then just add the we asked first data is equals PTR and ICT U then count stands for remaining count. So it so here we have the amount of elements that we can still access, and each time we make plus plus or advance by more than plus plus or advance by more than one, then we will see whether we still have here something that we can reference or whether we are already at the end. Okay, for equals and unequals, it will be very simple. We'll just compare p data is always outer p data. As a typo. Like, I think this is equals. Right, those as attribute. This one just gives us return asterisk p data. This one gives us return p data. So we call something here. Right, in the constructor, we want a few more data, so the asterisk ptr is equals p and PTR, so it can be null and size here. You count. I was to be. Let's go with this naming, and we can use the initializations in data to initialize one P data with the other P data, because here the compiler knows that if we're initializing something, it must be this one, while if we're using something, it must be that one. So it here allows us this way to use the same name. The body of the constructor could of course no longer work because it would be ambiguous. Here it is not, and the body itself is empty. Right, the constructor as such, sorry, the incrementer as such. So if count is bigger than 0, so if we can go further, then we our remaining count. This will be minus. Now we check if count is greater 0, so then p data plus and else. Oops. P data is equals null. So if sorry, not PTR, I want to be modern. Okay, and we need to return asterisk this. And the other one is pretty much the same, just that you make let's see, that must be greater equals count, and you just minus equals count. Here I go. This must be greater null. P data plus equals count. Else it's null, and return this. So this one is already completed. So now we are missing the functions which will actually give us some iterators to work with. So iterator begin const yeah, I think that might be quite simple. So one PTR, sorry, MPTR, PTR. So if there is something in MPTR, MPTR data and MPTR count. Oh, that is really lovely. GC and double point and end function we create next. And const return just iterator without any arguments, since we have well, we define default arguments at the beginning of null and 0. And the end iterator is just an iterator which has this set to null. That should be all. So let's see. We'll comment this out for int e and b. E is like a usually used for loop counts. So it's before value, or I could also just type our value. Let's go with that value. double point my array, any of those. Then you just copy this. It might need the array. Oh, no, that of course needs to be an iterator at this point, so we just go with auto. Or are I missing something? Right. It says begin, not found, but we created begin. No, we created not. We had a typo in begin. That's it should also work with int. Okay, then we don't. Then let's leave it at auto. No, something is missing. Just finish the other part. Doesn't like our unequal operator. Why? Oh, sure. I was too eagerly copy and pasting. And it's complaining about plus plus. It becomes no, it must not becomes right. Operator plus plus. No, it's fine. Now it should work. So like this. Yeah. Let's run. Well, almost. That is obvious. And this is obvious. As you see, the intelligence often doesn't show errors if they are in templates. So this is quite annoying. As you see, it works. And now we can also do the same thing manually. For auto e is equals my array2.begin is not equals my array2.end close e. And now if we would use like I++, it would not work because the other plus is not defined. And technically the operator as defined, you should use the plus before it. The STL operators accept both because you just define both operators, but here we try to be minimalistic, so we only implemented the bare minimum of what is needed for a reasonable operator usage, iterator usage, I mean. And here first now we will use the asterisk operator to get the value. And if we run it, then it works. So if you are thinking how to improve or how to implement your variants, if you make a variant which can hold a list of variants or a map of variants, then you could add such an iterator-based approach to iterate through it. And you also might want to use such a copyright approach on your variants. It is nice. It of course complicates things, so it's not mandatory. I think I didn't make it mandatory. I don't remember. I would need to read the assignment myself, but I usually don't make those parts mandatory. But they are a nice improvement. So if you would have enough time and want to make it particularly good, it would be great to use such a copyright mechanism. Especially that those variants will be passed around a lot. So saving on unnecessary operations is always a good thing. Now, what else are we missing? The standard STL vector gives us two more functions with regard to operators, which are very useful. It's the erase and the insert function. So the insert function basically allows us to insert data at the position of a given operator, while the erase function basically just erases one element from which the iterator points to from the whole data block. I think we could add this. It should not be too complicated. Although there is one caveat, so to say. It is a non-const operation. So our begin and end, as you see, are const. So you can always use them. Though this also is not always ideal, we should have two of them. A const begin, so something that gives us a const begin, and this const, and something that gives us a non-const iterator. Because we would, so here we could in principle access this I and modify it, which we don't really want. So we should, this is more complicated, let's not do it. The way this is, so there are limitations to what you can do with templates, and here we're reaching one of those limitations. Our iterator can be either set up that it allows certain functions when it itself is const or it doesn't. But we cannot make different functions in that sense always work reliably and reliably be unambiguous. So the STL implementation uses a separate iterator called the const iterator, which is basically the same as the normal one, just the types here are returned as const, and then depending on whether you want a const or not const iterator, then you can either modify the values or not. I'm thinking whether we can actually use one object to do both. We might be able to. Let's try it. That was the wrong key. Let's make again a copy here and have two of those, a const and non-const. So this one will be const. This will return a const iterator element, and this will return a non-const iterator. Those need always to change, so they must be mutable, so that we can change them even if we are inside a const function. This is always const, this is fine. Doesn't do anything. This one we will define as const because we want to use it on a const and on a non-const iterator object. Here as well, the constructor is always fine. And those we will just duplicate and make a const. I think it will work this way. Then I'm puzzled why the STL uses a separate object. I don't think we'll run into any issues. There might be like also historical reasons that they, at some point, not everything worked out perfectly. So the C was too old, so to say, it was missing some functionality. Because here now, if here our const thing and put this up there, then we should end up in the const situation. F9, F9, and then this F5. This yes, it doesn't like this. That's manageable. There's a complaint here as well, it just doesn't do it yet. And we might just copy those functions and have them return type const. That's the problem. Yeah. I mean, we might be able to, of course, fix this by casting, but I think what we really want here is to return those as const iterator. Then the iterator itself is const. And then we want the functions and non-const versions of those functions to behave differently. So I need here a non-const version. It should then invoke this operator. Here. That will still not be perfect. It will complain because the return type is const and the other one is not const. So we convert this reference in this and make an asterisk of that and then take the value. Might be that we need to add some more. Sorry, might be that we need to take here some more brackets, but I think it's not ambiguous these ways. It should maybe be fine. Let's run it. Yes, so here, if we step in, and we start here with the const version, and then once we're done, the end and some point we are here, and now we end up here in the we ended up in the non-const case. Why? And it's possible that there is some catch that will make this not work. First, we just go for begin, but that should mean that this is of type const. If it was const, then the author should take the right type, but here it did not. And you can write here const my array or int data something. Because it's the wrong thing. That's fine. And FVF, my returns. Yeah. And there we will take this without coins. And the auto keyword is failing on us. Let's see. Go into the const case. Then we end up here in the end, also const case. Then we should the comparison. That's also fine. Then we are in here, and then we end up in the const. Okay, now it's fine. Now we end up in the non-const in the const case. So it kind of fits with the auto, so just semi good, but it's good enough. Now, of course, if we continue and then look here in the other case, go in here and then we start in the non-const case. And comparison. And then at some point we end up in non-const. So this works as expected. Let's see. I think we're done with that. That looks like, I don't know, we forgot one important thing. The begin here, the non-const begin gives us an iterator which allows us to modify things. So we need to make it exclusive. The end iterator doesn't matter because this is just to find the end. But here we really want to make this exclusive. Okay. Good. So now we can add the erase function. And the way this erase function works is that it takes iterator and it returns the iterator on the next element after the erased object or on end. So this means you could use the erase function to clear a whole list if you want. So let's see. Iterator erase. We should use it, make it not capital. I like my functions to have capital letters at the beginning, but the erase, if you want to have some compatibility with STL, then we should keep erase to be lowercase. So it takes a iterator three. Would that thing take a const? No, it would not. It would make a copy. Let's go with a reference. But what we want to avoid is a situation where we take an iterator, it is const, pass it to erase, and the compiler eats it, accepts it. If we would have a value, it would just think, okay, I can just make a copy of the iterator and from const to non-const, and voila, you have your non-const iterator, and the thing works. Well, it shouldn't because it might not have exclusive ownership of the data. So if I use a reference, then whatever we pass to it must be non-const, and the compiler will not try to work around this on its own. Okay, so we have the exclusive ownership. Then we will need to have a loop which will move all the data around. So at this point, we kind of know that we hold this exclusive. That might not be true. Because we could have made begin, and after begin we could have called made an assignment of this explicit variable to another one, and at this point it would be shared again. So as you see, this copy and write mechanism requires some discipline, and it's probably one of the reasons why the designers of STL thought that it might cause more trouble than it's worth, because the idea of STL is it should be fail-safe, so that if someone doesn't use it properly, it will throw an error, but not result in unpredictable behavior. And here, the way this works without any else, I mean, we could, for example, have a check that erase checks whether ref count is 1, and if it's not, then it throws an error. Actually, that is a good idea. We should at least write this down as a comment, because this makes it really much safer. So check if exception. And the other thing is that, because generally when working with iterators, you are supposed to be very careful, because if you would insert something to a list, or array or object, where you have an iterator in use, then it might invalidate the iterator. Obviously, if it reallocates, then here this data will not be valid. But I guess the thing is that they just tell you the documentation that don't do insert on an iterator, or don't like erase things and then use any other iterator except the one that erased return you, which is now the list. But people might think that if they just do an assignment, that is fine, although they could just put this into documentation as well after having taken an iterator. Do not assign to anything else. But this really is much less intuitive than don't use this or that function. So I guess that's the reason why, because like you don't read the documentation to see if you can assign or not assign things. You read documentation if you want to find out what a given function does, or if you can use a given function in a scenario. Assignment is usually assumed to be safe, and this iterator mechanics here in a way breaks it. We could of course change it such that the arrays function itself would make exclusive, but then make exclusive might break our iterator. So then we would need to make exclusive work in a way that it will maintain the iterator. So basically our make exclusive would need to take a reference on the iterator, do its thing, whatever it might be, whether it needs to copy it on to nothing, and then if need be, then update the iterator for later operation. So we could do that, but I think for now, let's go the exception route. That is simpler. So, yeah. So for size t is equals e data minus PTR. We want to know the offset we are at. Data I is less than n PTR count minus 1 because we are removing one element, I plus plus. And now to the meat of the thing, PTR data from I, data from I is equals PTR data from I plus 1, semicolon, and then PTR count minus minus. And the way this works, our iterator remains valid, does it? When we erase the element, I cannot remember it, that we'll need that will need an improvement. So our iterator needs to change. The pointer remains the same, but the remaining count must be decremented by 1. Yeah, that will be correct. And then I just return a copy of I. Good. Should be correct. Let's see. Right, let's comment this out. And now let's go with auto x sequence begin x plus is equals 5. We want to delete everything after 5, and then, or rather, let's say we want just to delete 5, and then erase x, and in principle, like x. Let's say we want to erase everything after it. So for and here we check x is not equals and there is a bug in the code. There is a bug in the code. We need to do this check in addition. But we don't want to transfer this. So we shifted this, and if this is well, if rem count is equals 0, then this will be set to null, the last entry. We could maybe somehow smart and put this into there and make this somehow a helper function, but let's be more direct. Let's see. Oh, right, sure. That was nice. Oh, and the other one as well. Suck. It run. Dash. It's good. That is not great. It is invoking itself instead of taking the const version. Okay. That is solvable. That issue is solvable. Asterisk with brackets, more brackets. So we cast this to be a const, this, and then press it. The top one didn't fail for whatever reason. Top one worked out somehow fine, although it should have crashed as well. Oh well, it will work now, so let's run it. And it did a thing. Let's print everything. And voila, it erased as expected the element starting at element number 5. Okay, so our erase function works and it's behaving correctly. For good measure, let's add the insert function. Actually, don't remember the specification for the insert. On the vector at least in time. If this, what does this return? It returns again an iterator. Because the way our code works, the iterator for insert really will be unchanged. But since we want to behave the same way, then our insert will work the same way as well. So we have insert I, comma, and this is kind of like the append. So let's even, so whether it is used by STL this way or not, let's have two inserts, one that allows us to insert many and one that allows us just to insert one. So the other insert const reference value just return insert reference value comma 1 semicolon. Hey, now this insert. So the insert we need to make room. Basically, it's just like the append. No, it's not like the append. It does inserting. So let's think about how to do it properly. Return the iterator. We'll change the iterator. Of course, we'll do it. Rem count is plus equals count. Because we now have more elements, and we will most certainly change the pointer. So I p data is equals m ptr data. This will this is not, was also not great. To find the offset. This is the offset in data. And here, if we have possibly data plus this, so that we have the same offset, but the data will change because here we will reserve capacity is what was it? Append count plus Dingstar. Yeah. All right, I can make it prettier. No, I cannot. I mean, I could. Let's keep it like this. Stack reserve plus count. Count is there. Okay. So at this point, the pointer in the iterator is already invalid. So now we need to do two things. First of all, we need to shift the data after the insertion point further back, and the other one then will be we need to insert at the right position. So to do the shift. But first we will do the simpler thing based on our append code. So our append code 0 to count data, and this is not class b plus 1, but that's working. It inserts at the position where we are right now, and the element that was there is pushed one back. So yeah, data at position plus I, setting it 0 until count gets filled with this. And now we can steal that code. Let's split this a bit more logically. Stack. Right, we started position. We go. How do we go? We need to. The count hasn't changed yet, so here we will also need to increment count. Oops. Count plus equals count. Yeah, let's go with this approach. Okay, count here. Let's see. So at position is the element that needs to be shifted. So it will be static position. If you go to count, these are the valid entries, but we want to shift all of them. So no -1. Not erasing anything. We want to shift everything. And this will not work this way. We need to shift from the end. So we start with is equals count -1. We need a valid index. So I is greater equals pos and I minus because we are shifting from the back. Okay, so now we take the element at I. Right, we're shifting in this direction. We take an element I think so I will be the counter within the existing array. And then we want counter. Okay, no, that is too confusing. Let's do it differently. Let's go I is equal 0. I is less than making the helper variable. Size is not here. Rem for remaining. Remaining is count minus position. And we need a special case if iterator is end, which then just means we use append in it. Okay, so remaining is count. So we will now go from I0 to I remain, I plus plus. This is just a counter. So the way, the direction we are going here doesn't matter. Okay, so we need to take the value at the very end. So at count -1, the very end of our current thing is count -1. And we might take minus more if we go with rem. So let's, yeah, so -1 minus rem. No, sorry, -1 minus I. And then we want to insert it into the new position, which will be count plus count. I think count plus count -1. Right, why did we took the -1? Yeah, count -1 minus I. Minus I. This is correct. Just at the special case if E is equals end, then if E is equals end, then E and here we get end value and count. Yeah, we're running out of time and we didn't make any breaks today, so we should finish with this function. I hope it works. I'm not convinced it will. Let's remove this code part. Not the whole code, just this one. So let's just use similar comments. And x is insert punct e. Sorry, from insert at e, comma 555. Physics. Okay, let's run and see if it does. Okay, it's not compiling. Oh, the semicolon there shouldn't be there. I is missing. Yes, it worked. Added 5 before the entry and our iterator. Let's quickly check the documentation. Std vector insert what the iterator should point, the one that st returns. So what was that one value? Iterator pointed the inserted value. Yes. So wait. Yes. So given how our system works, for this case it's fine because like we shifted everything back, so the iterator kind of didn't change, except it did a bit. But kind of what it points to didn't change. But this is wrong. This is wrong. And how do we make this right? Need to create a new iterator because this will work. So this remaining will just set to 1 data plus ptr count. Let's see. Count is count -1. Okay, done. This should work in accordance to the specification. And I think for today this is enough. So we have 2 more lectures. I will have to think what we will do next. Either we'll create an own string class, based on this here, which probably won't be very insightful because it's very similar. I mean, a string is just an array of characters, and it adds a few convenience functions. So I don't think this will be very helpful. So let's not do that. I will think of something. I have this one very interesting thing to show you, as I mentioned already last time. You can use C to interact with C++ classes. It is just a very manual process. So if I don't come up with any better ideas, that will be what I will show you next time. Or of course, if you want me to show you something in particular, then you can tell me what you would like to see. Then I can show you that as well. So we will see each other next week. Have success with your final project. And if you have any questions in the meantime, you also can contact me by email at any time. Bye-bye.